Hey, good morning, everybody. Welcome to the reliability stage. My name is Brian Rapatini, and I arrived here last night from New Zealand. So it's my pleasure to be here today and to be hosting you in the room this morning and all of the wonderful lineup of speakers that we have this morning. So it's my pleasure to be able to introduce the topic today, which is the maintenance strategy optimization, uniting reliability principles and data science for significant savings. And Shereya Parashar from Woodside Energy, she is a reliability engineer, a mechanical engineer by degree, and a reliability engineer by pure luck. She fell into reliability engineering 6 years ago and is passionate in this field, bloomed organically. She is passionate about maintenance strategy, optimization, defect elimination, and using data to make data-driven decisions. And currently working in digital transformation, Shereya enjoys embedding reliability in digital tools, and she finds herself using reliability principles in her day-to-day life, living and breathing reliability as if it's a part of her. So I think there's a lot of key things in that intro that are incredibly interesting, and I'm just really looking forward to what you have, Shereya. So it's my pleasure to welcome you to the stage this morning. Let's give Shereya a hand as she comes up.
Hi everyone. For the last year, I have transitioned from being a reliability engineer by day to a reliability engineer day and night. How so? Well, I became a proud mum to my son, Ayan, and I found some surprising parallels between motherhood and reliability principles that I'll share with you today. The first one, I found myself being a detective, using root cause analysis to decipher why my little one was crying. Hunger? Diaper? Sleepy? What is it? Is it a combination of these causes? I was doing fault tree analysis in my head 24/7. Further to that, I became intimately acquainted with MTBF, mean time between feeds, and mean time between sleep. These were the critical metrics that dictated my life. And this is where it gets more interesting. I became a data collecting maniac. I joined the ranks of many other parents, apparently, collecting a huge amount of data on their kids. I was recording anything that I could. I was recording how much my little one was sleeping, how much he was consuming, his diapers, you name it. I was tracking it all. And this is a snippet of what a week looked like in my household from 6 a.m. to 6 a.m. It truly was 24/7 data collecting reliability project. So why was I doing all of this? By collecting all this data, it enabled me to draw insights and understand my little one better. I was able to make data-driven decisions. Ayan is my most prized asset, and I'm sure many parents feel the same about their kids. So I was able to better understand my asset and optimize based on his feedback. This meant a happier little one and less chaos in my house. So this is how reliability followed me into motherhood, and I'm here to extend it to our businesses today. I will be diving into how reliability principles unite with data science to optimize maintenance and achieve long-term savings for your business. So let's dive in. Looking after equipment is a critical task, and it doesn't stop for asset-heavy organizations. We need our equipment to be safe, we need it to be reliable, and at the same time, we want to minimize our life cycle costs. This in turn improves our profits and also impacts our emissions. How many businesses can say that they, hand on heart, are able to achieve this? This question becomes more and more complex when you have hundreds to hundreds of thousands of equipment across assets and across the world. And that's the landscape that Woodside operates in. It was this complexity and this necessity that really drove our business to think about how do we look after our equipment better, and how do we optimize the maintenance strategies? So what is maintenance strategy optimization? Simply put, it's doing the right maintenance at the right time with the right tools. It really is a balancing act of reliability, production, cost, and downtime, while always ensuring that we meet our safety targets and we're minimizing emissions. In the pursuit of optimal maintenance, we encounter several challenges, and these challenges I'm sure many other businesses face. Where are we maintaining our equipment too much or too little? How do we analyze hundreds of thousands of equipment effectively? What data do we need to support strategy optimization? Are we addressing our failure modes? How do we optimize with gaps in our data? And how do we do all of this efficiently and sustainably in the business? So these were the fundamental questions that we had to ask ourselves, and it drove us to innovate and develop our own in-house strategy optimization tool, named Ramp Plus. And I'm here today to really dive into the nitty-gritty of what this tool does so that you can leverage what we've done and apply it in your business. So let's dive in. Enter the optimization tool. The tool is built on a 4-step process, and it was built in hand with the process to deliver the outcomes. The 4 steps are broken down here. The first step is to find. We need a way to effectively find the equipment that is not performing well, and what I like to call bad actors. We then need to understand what's happening to our equipment. We need to review the data. We want to use our data that we've collected over many years to understand what's going on. Third, we want to optimize. This is where we take our knowledge and we do optimization using the data that we've got. And then finally, to finish it off, we have to efficiently apply this into our maintenance management system to actually see a saving or a change. So these are the core 4 steps, and I'm going to dive into them into a bit more detail. So starting with step 1, what are your bad actors? So this is where we face the first challenge. How do we analyze hundreds and thousands of equipment? And then how do we do this efficiently so that all our stakeholders who are interested in different cuts of our equipment are satisfied? Our approach involved breaking down our data based on our asset hierarchy. Very simple. We further classified this into business roles, equipment, and criticalities. So we really tailored this to our business needs. This allowed us to slice and dice over 200,000 equipment into manageable chunks. From here, we hit a second challenge. Where are we maintaining our equipment too much or too little? Where are those bad actors? So we need a way to be able to compare our equipment. We need a metric that we believe is reliable and available for all our equipment types. And for our business, that looked like maintenance costs and maintenance hours. From here, we applied the famous Pareto analysis, the 80-20 rule. We only have so much resources. We really need to focus on the equipment that's not performing so well. And the 80-20 principle can guide us with that. If we focus on the top 20%, we're hoping that we can hit 80% of the problems we're facing. Now, putting it all together, we came up with a very smart classification. So the Pareto analysis allowed us to cut our data into a matrix view. We all love matrices. And we had 4 distinct sections. that I'll take you through. So the very first quadrant that we're looking at on this matrix graph is what I call the not a bad actor region. We're happy here. We have equipment that is, we're not spending too much money or too many hours on proactive and reactive. The first red section right up the top, this is where we have relatively high reactive work costs or work hours compared to our reactive work hours or costs. So this region, we named it as potentially under-maintained. We may be under-maintaining here. Moving across, where we have high reactive and high proactive work or cost and hours, this region indicates that we may be maintaining our equipment incorrectly. We're spending a lot on both types of maintenance. And then finally, low reactive work, but spending a lot on proactive. So we're doing a lot of proactive activity, and potentially here, we're actually over-maintaining. And there may be opportunity to look at and optimize our maintenance. So these 4 quadrants allow us to really classify our equipment very quickly and understand what could be happening. And that's the first step. So now we know our bad actors. We know where they're sitting on our classification. We now need to dive in and understand what is actually happening to that equipment. We really need to probe its behavior. How do we do that? And how did we do that? So our approach was to look at our maintenance data, so look at the equipment history, and really take that equipment history, do some data cleansing to really understand the failure pattern behind it. We needed to understand when that equipment was installed, how long it lasted, when it failed. Very key data. By having this data set, we put this into a survivability model. You may have heard of it, the Kaplan-Meier estimator. So this describes the behavior of your equipment, and it describes what's the probability of it lasting based on past data. This then fed into what reliability engineers like, the weighable parameters. So we were able to get out the weighable parameters, mean time to failure, mean time to repair. And we were able to compare this to industry standards. So what we did here was actually use our own data, our equipment history, to see how that equipment was failing and comparing it to what we expect in the industry. So from here, with our weighable parameters, we can take the beta parameter, which describes the failure pattern, and have a look at the bathtub curve that I'm sure many have seen before. The beta parameter helps indicate where we're sitting on this bathtub curve and also alludes to the type of strategy that we can employ. So for early life failures, an appropriate strategy generally is to understand why our equipment is failing so quickly once it's put into service. As we move into the random failure region, an appropriate strategy here can look like inspection and testing on condition to understand when we can do maintenance or replacement on our equipment. And then finally, the wear out region. As our equipment gets older, it starts to wear out. So an appropriate strategy in this region looks like a time-based or condition-based replacement. So really understanding this beta parameter helps us understand how we should look after that equipment, an appropriate strategy. So now we have an understanding of our equipment failure pattern. We need to untangle the complexity of how our equipment fails and what's caused it to fail. Now this is a pretty hard question sometimes, and what we found with our company data, that a lot of the failure modes and failure causes were hidden within the rich text of our maintenance data. There was codes, but also there was a lot of rich text that talked about failure modes and failed components. So we harnessed we harnessed the power of word cloud functionality. Word cloud allowed us to read the long text of our notifications and pick out all the relevant words relating to that equipment. We enhanced it with ISO 14224. It's an oil and gas standard which states all the different ways common equipment can fail. So with that, we could pick out very quickly for a pump across the board what was happening. So we're seeing impeller failures, O-ring failures, bearings. And the failure modes that we also saw was perhaps cavitation, blockage, erosion. So it was very quick to pick out the key words that we're interested in. So now we reach the final two steps. And this is where we piece everything together. We have a profile for our equipment. We knew that it was in the over-maintained region in our bad actor analysis and Pareto analysis. We understand that the most failed component from our history is the impeller. The failure cause is also where. And the mean time between failure from our failure data and modeling shows 4 years. And a weighable parameter is beta 2, so wear out failure. So piecing all these bits of data together and then having a look at what we're currently doing, which is a 2-yearly replacement, we can see a clear gap. We can see that there's optimization opportunity here that our tool has showed us. And the potential here is to actually extend our maintenance frequency from 2 years to 4 years and align it with any shutdowns that we have. So further to this, there may be some scaling opportunities. We've just looked at a pump. There may be a similar pump across our other assets. So we can apply this strategy perhaps to other parts of the business too. And that is a direct impact to our costs. So in summary, we've used Pareto analysis and smart classifications to understand the equipment that's not performing so well. We have used lifetime modeling, weighable, and data mining to understand the failure modes and the failure patterns sitting behind the equipment. We have pieced all of this together to understand how we can optimize our strategy and use a data-driven approach. And finally, we need to make those changes into our maintenance management system. Now, we all know a tool's only good if people are using it. So how did we take this tool to the business and have seamless integration? I'll take you through that. So firstly, we needed support from our leaders. Our leaders needed to be aligned with the intent of the tool and what we were trying to do. From there, we were able to train our key stakeholders on the tool and the process. We held dedicated optimization workshops. We had our engineering, maintenance, and operation folks put together in a room to dedicate their time for strategy optimization, supported by reliability engineers. We embedded this into our processes to ensure that it wasn't just a one-off task, it was a way of working, continuously improving on our equipment maintenance strategies. And the outcome? What we saw was improved equipment efficiency, improved equipment reliability, reduced emissions, and savings. And at Woodside, that was in the figure of sevens. So a significant amount of savings from this piece of work. So what's the future? Where are we now with the tool? The tool that we created was an MVP, a minimal viable product. And showing the success to the business meant that we got quick buy-in. And as a result, we were able to expand on the tool and just make it smarter and better. So this is what we've been doing. The first step, finding our bad actors, we actually put in smarter metrics to find those optimization opportunities. We know there's other ways to find equipment that may not be performing well, so we've added those in. Second, analysing the data. We have a diverse range of data sources, hosting, equipment, data. So we needed to pull all of these together. And this looked like the HAZOP LOPA data, maintenance histories, all the different changes we've made in the past for this equipment. So we pulled a diverse range of data together. Step 3, the optimisation piece. We've built in FAMICA and RCM modules. This allows us to record the outcomes of our strategy reviews, and it retains a digital history of this. And then finally, in the step 4, realising the benefits, we've started looking into how we can automate the processing of these changes. So how can we make these changes much faster in our maintenance management system? And how do we scale this across different assets? So in conclusion, the principles of reliability engineering are not just theoretical concepts. I've unknowingly used them in my motherhood journey and applied them in the field of maintenance strategy optimization. We are in an era of advanced algorithms, machine learning, AI, predictive maintenance, real-time equipment data that's really transforming the asset management space. There's a lot happening and it's really exciting. But we must all remember that the key and the core reliability principles are the foundation of this work. When things get complex, come back to the basics because they really work. Now that you've witnessed reliability and data science unite, I can't wait to hear how you apply this in your business or your parenthood journeys. Thank you.
Hey, thanks, Shereya. That was amazing, right? I always enjoy listening to real-life examples where, especially reliability engineers, are able to take information, turning it into meaningful knowledge that allow for actions that deliver better results. So well done, congratulations. Now we do have some time for some questions, but if you've got a question, put your hand up and somebody will bring a mic to you. Okay, here we go.
Hello. With the example of the pump, the current strategy was to change the pump, or to service the pump every 2 years. But the data showed that you have a mean time between failures of 4 years. So that means that you have to have failure data to be able to get that. But if you were servicing every 2 years, how do you get that number?
So a little background. So Woodside's been in operation for over 30 years. So we actually do have 30 years of historical data on the pump. So yes, you need statistically enough data to be able to make those data-driven decisions. Did everyone hear that? Okay, thank you.
During your presentation, there was one slide which talked about word clouds and trying to read from the long text of notifications, trying to build the failure data. Now, it's not always that all types of equipment have such good data to drive your decisions with. So how do you go about just the general cases where there's not much information in the notification, and how do you go about when you have very less data to go by?
Yeah, that's a really good question, because you can only make data-driven decisions if you have good data in the first place. So I'll answer in 2 key parts. Just going back to the slide deck around the actual reliability side of things. So when we try to understand the weighable parameters, the output of doing all of this, we do some grouping, some failure grouping. So we want to find like equipment. So we know that with one pump on the plant, we may not have enough data to make any informed decisions. But what we do know is that we do have a number of pumps on site that are very similar operation, similar type of pumps. So we can do some smart classification. So we can grab like equipment, like pumps, and use their data combined. So that's the first part. And then secondly, around the word cloud. The reason we even use word cloud is because we know that in our notification and maintenance data that we don't always have the correct coding. So the word cloud was a way for us to use that rich text and actually draw upon what could be happening, because a lot of the time we're typing and we're saying that we need to fix this and do this because of this, but we may not have coded it properly. So that's why we use the word cloud functionality with the groupings to get more data.
Tell you what, and when you're done, can you pass it behind you?
Yeah, thank you. I love the simplicity of the word cloud, but I'm really interested in the data cleansing that may have gone through with that. You know, there's 7 different versions of writing pump, and anything that you may have had in that respect.
Yes. So obviously there is, we do write things differently. It's all, free text. So we have to be smart with how we grab that information. So that was all built into the tool. So we use data science to help us. So I guess we really had to dive into the data. So we had a good understanding of what the data looks like. Where do we potentially see some issues if we were to use word cloud functionality? So by understanding the data, we're able to tailor our solution. So if we know that we're perhaps saying pump but spelling it wrong, our word cloud was able to actually pick up those words and cleanse it. Yeah.
Hi. Where in this process do you take into account business requirements? So I guess on the plant, if it's ramping up or ramping down, that will then affect the wear of your components. I'm just wondering where that fits into this process.
Let me have a think. So you're right around the business requirements. So the 4-step process was very simple. You could see that we're really just picking up things that were standing out to us as high cost or high proactive and reactive. And as part of the future, what we started working on was pulling in other metrics to understand where we're performing poorly. So looking at historical performance trends, process trends, all of that actually fed into here. So we were able to dive into the process side of things as well. So not just the equipment side and the equipment failures, but what we were doing on the plant at that time.
Okay, we still have a couple of minutes if there's any more burning questions. Here we go.
Has the tool changed people's behaviours in how they write information in the notifications or in closing comments? Is this driving a cultural change as well?
That's a really good question, and that's something that I'm very passionate about, because as reliability engineers, we cannot really make data-driven decisions if the people that are writing our notifications and recording that failure data are not doing it correctly. We simply cannot do our work, our job. So a big part of the rollout was to have the key stakeholders here involved. So we had our maintainers, we had operations, and there are 2 key stakeholders that do put in maintenance data in our system. So I guess the hope was that with the training and the understanding of why we're doing this, and the drive from the leaders, that has cascaded to those people that actually record our failure data. So I think in terms of cultural change, that takes time, but I think sometimes you need to show where that data is going to be used and what we're going to do. So by seeing the actual impact, seeing the savings, seeing the reliability improvements, we've got something tangible that we can talk to now. So it's the first step.
Thank you. Last question.
I know you're using the pump as a bit of an example, but you've gone outside the OEM specifications. What was the process behind that, and did you engage with the OEM to go outside those specifications? Because sometimes it's not real common practice.
Yeah, absolutely. So it's all based on risk for us. So, you know, our OEM does tell you, you know, when you should perhaps maintain certain components that may not be critical to like the operation, I guess. So for us, we do look at what the OEM specifies, and we do make like a risk-based decision on that. And if we need to consult with them, we do. The key here is that we're using our 30 years experience data. We're using it on our plant. OEM does provide, I guess, a guidance, but we're using our own data to actually change the maintenance. Yeah, good question.
Thanks very much. Let's show our appreciation once again to Okay, now for those who didn't get a chance to ask a question, Shereya will be at the Knowledge Corner down at the Prometheus booth downstairs. So if you've got other questions, head down there, she'll be there to answer them. Okay, thank you.